Let's start, please.
So my talk will be about special functions which arise in the studies of supersymmetric gauge theories in 4 dimensions in accordance with the tradition which I think Gelfand was a fierce advocate of. Interesting mathematical problems come from physics, and maybe vice versa. So I will try to give a mathematical version of the story which has its own physical interest. And let me first start by saying what is the BPR-CFT correspondence. This is not a mathematical statement, it's a principle, it's a physical principle, which states that the correlation functions of chiral observables. For mathematicians, the word chiral means these are a homology of some supercharges. In supersymmetric gauge theories in 4 plus epsilon dimensions. Are only on the movable part. Oh, I see. Sorry, I didn't see. So the principle states that these correlation functions are actually matrix elements or traces or functions of that kind of some infinite dimensional algebras, such as Cosmodi algebras or quantum affine algebras or Virasoro or W algebras, and possibly the deformations in some representations. So these are already some special functions which typically arise in a 2-dimensional world of 2-dimensional conformal field theories and possibly massive integrable 1+1 quantum field theories, such as Sine-Gordon or more general Toda. And an example of conformal field theory which seems to capture such functions, the theory of free fermions, WZW models, and Liouville theory or Toda theories, non-defined Todas. So these matrix elements correspond to something which is called conformal blocks. So these are chiral So these are chiral parts of correlation functions of two-dimensional conformal field theories. So this principle is based on observations originally. So this is an example of hiking in the mountaineering region, where you just see some nice spots. But the amount of evidence which has been accumulated over 10 years, I would say, maybe even 20 years of work in this domain suggests that there should be a theory which really explains all of that. And of course, there are physical arguments why such a correspondence should take place. But these physical arguments rely on the conjectures in the physical sense. So the conjectural existence of some theories which we don't really know how to describe in a conventional quantum field theoretic language. So today I will present some simplified version of this story. Namely, I will define for a class of theories in 4 dimensions the generating functions of such chiral observables, and I will tell you what is known about the representation theoretic representation. And then I will show that in some cases which are perfectly fine from the on the gauge theory side, so this is the BPS side of the correspondence, and this is the CFT side of the correspondence, you should not be able to package these functions in the representation theory of algebras of Kac-Moody size, and you would most likely need to go to higher dimensional algebras like toroidal algebras, but not in the sense of the quantum affine for affine algebras, but something really bigger. Hopefully I will be able to convey this point. So first, let me describe the cast of characters for this blackboard. And so we'll start with a graph, actually quiver, which has a set of vertices and the set of edges.
Not more than one edge.
Exactly. Yeah. So I will have a tool which allows you to have multiple edges, but in this sense it's at most one edge precisely. And of course, you have two maps, just these projections, which send the edge to its source and its target. So these are inlet edges. And now we will need a piece of linear algebra. So I will have, I need a pair of what I will call the gamma-graded vector spaces. So what it means is these are direct sums whose components are labeled by the vertices of my graph. There must be a better way of phrasing this, but I didn't find the proper algebraic formulation. And I will also have a vector space which is graded by the edges. And so these vector spaces are to be thought as of the multiplicities of edges. Now, there are some requirements that the dimensions of the spaces V, which I will call little v, have to be strictly positive, and the dimensions of the spaces W can be 0. And so Say again? Finite dimensional. Yeah, I will. In this talk, I'm going to talk about finite quivers and finite dimensional spaces. So it seems, well, okay, so you could have multiple edges with multiplicity 0. And then I would need some parameters. So my parameters would be a matrix A, a collection of matrices, actually. So this is so this is really a collection of matrices acting in graded components. The notation is such that if this quiver gamma came from a representation theory of a finite group with vertices labeling the irreducible representations, then this would be really the gamma covariant endomorphisms. But for now, I don't want to assume that there is a finite group attached to this problem. And in general, there won't be. But I'm using the same notation. So I also will have a matrix M, which is a similar object, except that it's in the gamma covariant endomorphisms of W, and little m.
So gamma covariant doesn't mean kind, right?
It's just notation. So what I really mean is that M preserves the grading. So M preserves the grading. So maybe I should call them graded endomorphisms. Okay, in the main example, the multiplicities of my edges would be equal to 1. And so these little m's would be just complex numbers attached to the edges. Now, this is not all the data which I need. I need, in addition, a map tau from the set of vertices to the upper half plane and its exponentiated version so to each vertex I have a complex number of absolute value less than 1. And the last parameter in my problem is a pair of complex numbers. And so given all this data, one can define a certain function, which will be a function of A, M, little m, tau, and epsilon, which has some quantum field theory definition, which I will skip. And then there is some quantum field theory theorem which says that this function is equal to an integral. It's given by an integral over some modular space, which I will now describe, of the equivariant Euler class of some sheaf. Now I need to describe this modular space and the sheaf of the modular space. Okay. So M would be the modular space of gamma-graded torsion-free sheaves, torsion-free framed sheaves on CP2. So gamma-graded means that so that my sheaves are really direct sums of sheaves labeled by the vertices of my quiver. Framed means that the restriction on a line at infinity, so I want to think about CP2 as C2 with a line, is isomorphic, and the choice of isomorphism is the choice of framing, to a trivial holomorphic bundle over P1, which is also gamma graded, which is given by V. So it's V. This is my framing. And apart from that, this is only so so we take all we look at the modular space of all such sheaves. So this is a disconnected. This modular space has many components, which are labeled by the second Chern classes of the graded components. So M. Say again?
Do you assume that they have determinant 1 nearby? Because if not, then you also have the kind of degree.
No, I think the degree is forbidden by this condition. Yeah. So they have degree 0, and so the sheaves which belong to the component Mk have second Chern classes fixed. So this integral is now understood as actually the sum over all these components. And then we introduce a weight. So Q to the K, by definition, is the product Qi to the power Ki. So this is the use of the parameters tau. So remember that Q is e to the 2 pi I tau. Now, so I defined what M is. Now I need to define the sheaf F. It's the so-called abstraction sheaf. So F. Oh, I made a mistake. Okay, well, I shouldn't have erased this. So let me denote by E also the universal sheaf. And so we have a projection from the modular space times CP2 to the modular space itself. And so this universal sheaf is defined up to multiplication by line bundle on M. This freedom will essentially disappear in what I'm about to define, so I will not worry about this. There is a version, there is still visible plus epsilon, so what I'm defining now corresponds to the 4-dimensional gauge theory. There is a version which corresponds to the 5-dimensional gauge theory where you deal with K theory. Instead of integrals, you take the push forward in K theory, and there the choice of line bundle is important. And it corresponds to something which is called the Chern-Simons couplings in 5-dimensional gauge theory. But today I'm not going to talk about it. So F is defined as follows. So you take the graded morphisms from E to E tensor B. I will now explain precisely what this means, plus you take the morphisms from E to W viewed as a constant sheaf over CP2 and M, and then you take the push forward, the derived push forward. And so what this guy is. Well, remember that B is a collection of vector spaces which I assign to the edges. So the morphism from E to E tensor B, which is gamma equivariant, is just the morphism from the sheaf which corresponds to the source of the arrow to the sheaf which corresponds to the target of the arrow. So what this guy is just the direct sum over the edges x tensored with the trivial vector space BE. I need to keep track of all these vector spaces because my integral in all my classes, characteristic classes, are equivariant with respect to the action of these groups, and the morphisms of V, and the morphisms of W, and the morphisms of B. And A, M, and capital M and little m are equivariant parameters. And so this is understood in the sense of equivariant cohomology, where the group is, so the group is the product. It's the endomorphism of V cross endomorphisms of W cross endomorphisms of B cross GL2. So GL2 is just the symmetry of CP2 preserving the line at infinity. And so capital A corresponds to this group, capital M corresponds to this group, little m corresponds to this group, and epsilon corresponds to this group. Say it again? Sorry, the group is, of course, GL, of course, thank you. But the equivariant parameters live in the Lie algebra. Okay. So, and this guy is, of course, the sum over all vertices, x.
X is a sheaf.
It's a sheaf. So it's a sheaf. Yes, and I take its I take a direct image. Yeah. Okay. So so you get this. So this is actually it's a complex of sheaves, and so you take. When I write the Euler class, I take the ratio of the Euler classes of all its of all the members of this complex, and this is all equivariant with respect to the symmetry group. So this is some kind of rational function of all these parameters, and then I'm supposed to sum over all Chern classes of all charges, and well, I get what I get. Well, the first question which one should ask is whether this is a formal power series in Q or whether this is a function, because I call it a function. So there is some condition on the graph and on the representation of the quiver which I started with, which guarantees that this is going to be a power series with finite, with a non-empty domain of convergence. And this condition in physics is called the condition of asymptotic freedom. This is something which is worth a Nobel Prize. And it actually, so it's some set of inequalities. Yes. Yes.
I missed. How does this integral depend on AM?
This is equivariant. It's an equivariant integral. So this modular space is acted on by the group of GLV gamma, which changes framing, and then all these vector spaces which enter this definition are acted on by these groups, GLW, GLB, and so I'm doing the integral in equivariant cohomology. The space is smooth, yes. Right. And so the space is non-compact, though, and so this integral. the ranks of these groups. So this is finite. Yeah. So the action of this group is of course is not free on M, and therefore so there's and this is how actually this integral is computed, because by localization on the fixed point formulas, using the fixed point formulas. And so that actually becomes so this integral becomes a combinatorial object. So bringing another topic of yesterday's recollection section, that in fact there is a lot of combinatorics associated with this partition function. But before I go there, I should first state what are the conditions on my spaces V and W for the series to converge.
How is GL2 acting? Is it acting as C2 factor?
Yes, on C2.
But there is also a GL3 action.
No, you see, my construction, I have to fix. This has to be fixed. The line has to be fixed. So. Okay. So what is the condition? The condition is that twice Vi minus Wi minus so this has to be greater than or equal to 0. And in fact, if you know how to solve these equations with equality, this is called asymptotically conformal theory. Then it's easy to produce all solutions to inequality by taking the space W just smaller. So the question is, what are the solutions to these equations?
That is guaranteed that it's got K from which it is non-zero line some O.
Yes. I mean, well, it's so K already lies in some cone because these are positive numbers, chain classes. But we need Q. We need to be able to majorate the terms in this series by some exponential, which decaying exponential of Q, and this is not always guaranteed. And so, in fact, if this equality is not satisfied, if the inequality goes the other way, then you might get. I mean, it's another interesting problem which hasn't been explored. These numbers grow factorially, actually, in the opposite case, and so you may get something which is Borel summable or something which is not Borel summable, and if it is. But even if it is Borel summable, you have ambiguities which related to the singularities, and there's an interesting story, on the physics side of it. What is ambiguities? What do they have to do with the definition of the theory?
Does it depend on the conjugacy classes of A and A?
Yes. In fact, there is a sort of a sloppier way of keeping notes of keeping track of these parameters by thinking of that A, M, and little m belong to the vector spaces themselves, because it's just you could assume that these are diagonal matrices.
But what is the point of using matrices if it only depends on the algebra?
Because well, I will need to write some expressions which involve matrices like determinants and things like that. It's I mean, you could just write the collection of numbers, but then it's going to be very, very long. Yeah. No, but that's the point. I mean, so this is the nature of these parameters. These are elements of the Lie algebra.
Eigenvalues are not rational functions, elements of matrix. Yeah, but
Okay. So first of all, let me just remind you what is the classification of the solutions of the equality. It's a famous problem, and the solution is the solutions are of two types. Type 1, when W is not equal to 0. In this case, gamma has to be finite AD, Dynkin diagram. at least one. And type 2 is when W is equal to 0. And in this case, gamma is affine. AD Dynkin diagram. In fact, in this case, gamma is the what's the name? It's Mackay graph of the finite subgroup of SL2. In this case, when W is equal to 0, you don't have much choice for the dimensions of the spaces Vi. They are all proportional to Dynkin labels, which are also the dimensions of reusable representations of the. Yes.
Doesn't depend on B at all.
No, so B will have to be one-dimensional at most in this case. So gamma is a finite Dynkin diagram, and dimensions of B are equal to 1. But low cases.
Yeah.
From the way so if I get to some sort of solution of this problem, you will see that there has to be a modification of this problem which will allow any Dynkin diagrams, not necessarily simply laced, for example, because the solution will involve representation theory of the corresponding ADE groups, and there is no difference between the representations of ADE or BCG. So it's just some lack of imagination on our side that we don't know what to do with this. By the way, what I'm talking about now was done in collaboration with Vasily Pestun last year. So, okay, so suppose we are in one of these cases, and then we want to get some understanding of what this special function is. Is it related to any elementary special functions, or is it something new? And it turns out that there is a useful object which you can study together with this function, which is also, so this is a generating function of that type. Where you have, in addition to the Euler class of the sheaf F, which I erased, you also have also the equivariant Euler class of how to describe it. So you take the universal sheaf and then you sort of tensor it with a skyscraper sheaf. Located at the origin, at the fixed point of rotations in C2. So if E were a bundle, I would just say you restrict you take the fiber at the origin, but it is not a bundle. So this is it's a trickier object, and I take the equivariant Euler class. So equivariant Euler class is the same thing as a Chern polynomial, but if I said that it's a Chern polynomial, it would sound like it's a polynomial, but in fact it's not a polynomial in X. This is so. Again, if it were a bundle, a locally free sheaf, this would be just the Chern polynomial but it is not locally free, and so it is not. It's not a polynomial. It's actually it's an interesting function of X, which so it behaves as degree Vi polynomial in X when X goes to infinity, but in fact it has it's an infinite series.
How does I enter the right place? There's missing.
Sorry, EI. So it was a sheaf on the product, but so S0 is it's a sheaf on CP2, which is it's a skyscraper sheaf at the point. So you get and then but then you also do the push forward. Sorry, so I should have said that. Yeah. So it's a fancy way of just trying of doing as close to restricting it to a point as possible. And so from these functions, yi will reconstruct the function z itself. It's, maybe not today, but eventually. So there is some set of equations which you can derive on these functions y, which look complicated, but in the limit when epsilon 1 and epsilon 2 go to 0, y's can be found algebraically in the following way. So remember that we have now at our disposal a Lie group, either a simple finite-dimensional Lie group AD in the type 1 case, or a Kac-Moody group in the type 2 case. So suppose, so I have this, so, and in this correspondence, the vertices of my quiver correspond to simple roots or co-roots of this, let me call generalized Kac-Moody algebra. So let me define the following object. I will take my function yi of x and raise it to the power negative ith co-root of the corresponding Kac-Moody algebra. Take the product over the vertices. And then also there is a correction factor. So what I've defined now, that we call g of x, it's a function of x with values in a Cartan torus of, so g sends x to an element, so g of x is in a, it's a maximal torus of the corresponding ADE or affine AD group, with a slight complication coming from the fact that these are fundamental weights, co-weights. So I actually have to, I cannot embed them. Second? I have to take a cover. So I have to take what we call the, there's this conformal version of the group where you extend, so to the group G, you can associate its conformal version, which is an extension by C star or C star cross C star over a center. So for a spin, well, it gets tricky. So for spin 2R, you have to take 2 C stars actually. So, but it's a minor complication.
So what kind of, is this y affect some kind of series with the big leading term?
Yes. So it starts, so at infinity, it starts as it behaves as a power, just exactly x to the vi, plus subleading terms.
And you raise the power at that by using this.
Yeah, so you take a logarithm and then yeah. And so the condition of asymptotic freedom actually implies that when you look at the leading powers of x at infinity, they cancel. Because so the leading power here is x to the wi. So you'll get x to the w lambda check minus vi alpha check. And this is 0 because of this equation, actually. Mi, this one. So Mi was a matrix in the W space, in the Wi space.
So what do you mean by asymptotic freedom? This where you try now doing algebraic theorem. What does it mean?
So it means that this group element approaches a constant at infinity. So it approaches some element G infinity. Okay, so far this is just some formal construction, but the solution which describes the asymptotic of this function, is in the following, that if you now take the character, any fundamental character, or let me say it differently. So in this way, this group-valued function, g of x, which I defined, is well defined at infinity. So it approaches a constant, and then you can expand it in the power series around infinity. But as you go inside in the x-plane, at some point you will start getting some cuts. So it will not be well defined. But the nature of this series is such that as you go around some singularities, G transforms by the Weyl group action. Weyl group action. So by simple reflections, actually. And so if you take a character, if you take a Weyl invariant function, a conjugate invariant function, this will be single valued. And so this is essentially, up to some normalization factor, which is, I can write it for completeness. It's different. It's J. Times a polynomial. So this is just a polynomial. Any type. It works for both cases. So in the Kac-Moody case, this factor is absent because then W space, this is determinant in the space W. And so these are the characters of the. This is a function on the torus of Kac-Moody, but these are the characters of integrable of the highest weight representations of Kac-Moody. And so you have a set of equations labeled by the vertices of our quiver, which determine these functions y in terms of some polynomials. And you have finite amount of data in these polynomials, and that determines the rest. So what is the geometry of that solution? Well, the geometry is kind of cute. Let me describe it in the affine case. So geometrically, we are saying that to each point in the x line, we have a conjugacy class in the Kac-Moody group, in the AD Kac-Moody group, which is also. And this is, by the way, when I talk about Kac-Moody group, I mean the loop group with the central extension of the loop group extended by the C star of rotations. And so these conjugacy classes are in one-to-one correspondence with holomorphic, now finite dimensional AD bundles on the elliptic curve. This is for type 2. Yes. Yeah. So there is a shift generator there. And so it's an elliptic curve whose complex structure is determined by my parameters qi. And the formula is that this is the product qi to the power a. This is you read it off from here, actually. AI are Dingin labels. These are the coefficients of the expansion of the maximal of root in simple roots. So they're all 1, 1, 1 for A type, 4 ones, and the rest of them are 2s for the D type, and then they're more interesting for the E type. So what do we have? So we have that for each point x, we actually have a holomorphic bundle on the elliptic curve. And almost for each point x. So because we describe this using some polynomials, what this object is actually, it's a quasi-map. So more precisely, we get a quasi-map from P1, where the x variable lives, with marked infinity to the modulus space of bundles, G bundles on elliptic curve. So I will keep calling this GAD. With some condition, with some restrictions.
I thought X is element in the torus.
X is a number.
Little x is a number. X was the argument of this function y. The element of the torus is g of x. So g of x is what defines this holomorphic bundle. It's a transition function. These are semi-stable bundles, right? So this is actually, in terms of a finite dimensional torus, it's the quotient of T cross T by W. But T is compact here, but we need its complex description. So this is actually the quotient of the elliptic curve tensor, the weight lattice by the group, by the rank. Okay, so we have additional restrictions on these quasi-maps, namely what I said about this g of x behaving approaching constant infinity, and so it has a well-defined expansion, means that near infinity, this quasi-map is actually a map. It's a map near infinity, and its image is fixed in terms of my parameters qi. So remember that the number of vertices in the affine thinking diagram is r plus 1, where r is the rank of the fine dimensional group. So one of these parameters, so this combination of the q's define the elliptic curve, and the rest r parameters define a particular holomorphic bundle on the elliptic curve. And so this particular holomorphic bundle is what my quasi-map has to approach at infinity. If you work this out more precisely, then you also get like the first jet, actually. The first jet is fixed. So the image at the point and the tangent vector. This is fixed in terms of the little m's, which I didn't mention precisely. Okay, so this space of quasi-maps with these conditions, actually it's a vector space. It is precisely the space of coefficients of all these polynomials. But this function z provides this vector space with the additional structure. Namely, it endows it with the so-called special geometry. So
one function g of x can have a singularity, right?
How should I state this? The point is that my polynomials t of x, they, roughly speaking, they can have common zeros. So you see these chi's, these are sections of some line bundle over the modular space of over band G. Band G is a weighted projective space. And so in this way, so Ti's are really just the homogeneous coordinates on this weighted projective space. So when you define a map to projective space by saying that the homogeneous coordinates are polynomials, this is not always a map, because if they have common zeros, then at this point you're in trouble. So it's a map. It could be a map of lower degree, defined everywhere except at some finite number of points. But then at some number of points you have additional structure. We called them freckled instantons a long time ago, but before we learned that these were defined by Greenfield as quasi-maps. So by we I mean Losyev, Shatashvili, and myself. Anyway, so there is this additional, so there is a special geometry on B, which is the space of this space of quasi-maps, for which A's, so the A's which I was sort of quiet about, and so A's provide, these are special coordinates. And this partition function, in the limit which I described, has an asymptotics with some function f of all the parameters except for epsilons. And then the derivatives of f with respect to these parameters A provide the second set of special coordinates. So
Is it specific analytic?
there is no elliptic. Oh, sorry. No, this is specific for this kind of problems where you have this function z and you study its asymptotics. Then it turns out that the original arguments of z, which came from equivariant parameters for the framing, and the derivatives of the residue of the logarithm of z when epsilon go to 0, they actually form a set of special coordinates which are defined up to an action of some symplectic integral group. But what I just explained is that for the problems where z comes from the quiver with all this data, the space where the A and DF over the A define coordinates is the space of quasi-maps. So it's a theorem that that in this case this space of parameters is a space of quasi-maps. And then, but then there is a general scheme for where such a set of coordinates come from. These are algebraic integrable systems. So there is some algebraic integrable system for which B is a base. So now we are sort of working backwards. We need to guess what is a holomorphic symplectic manifold which projects down onto B with Lagrangian fibers which are abelian varieties or can be compaxified to polarized abelian varieties. Well, you look at now it's a little bit of guesswork. So you have your base is a space of quasi-maps of P1 to the space of bundles on the elliptic curve. What should be the total space? Well, B doesn't have a Poisson structure. B has a geometry. It actually has a metric which is constructed out of this data.
You see the special coordinates are AIs and the tools.
Yes.
So
It's an exhaustive set of coordinates. You can locally on B you can choose half of this whole data. There is many choices for the half, and these halves are glued together by integral symplectic transformations. So that's a rigid structure. Okay, so you see that for each point, if you're dealing with actual map, for each point on P1 you have a bundle on E. So if you glue them together, you get a bundle on the product of P1 and elliptic curve. And now what's so special about elliptic curve? If instead of E you had the higher genus curve, then basically you wouldn't have any freedom in gluing the fiber-wise bundle into the overall bundle, in the bundle on the surface. But on elliptic curve, the bundle has automorphisms. So there is a lot of ambiguity in how you lift. And this ambiguity is actually the fiber of this integrable system. So this holomorphic symplectic manifold is the modular space of bundles on P1 cross elliptic curve. But of course, as it is, this would not be a symplectic manifold because P1 cross E is not a symplectic surface. So you need bundles with some trivialization on the fiber on at some, let's say, over infinity cross elliptic curve, but not just a trivialization because the holomorphic symplectic form, the meromorphic symplectic form, has a second order pole at infinity. So you need a trivialization at the, I don't know what's the right notation. So you need a second infinitesimal neighborhood of the fiber at infinity. So this is what covers the choice of this is what covers the fact that we had fixed bundle at infinity and the first jet. So this first jet translates to the trivialization of the actually first infinitesimal neighborhood. Sorry, it's not the second infinitesimal neighborhood. Okay, so this is an integrable system, actually. It's a space of bundles on the surface. The surface is fibered by elliptic curves. And there are some restrictions on the behavior of these bundles near infinity, cross elliptic curve. And that you can project by restricting your bundle on each fiber, you'll get a projection to the space of quasi-maps. So this space is, of course, symplectic. This is the way physicists would write a symplectic form. Oh, yes, you're absolutely right. Yes, I forgot. Of course, I'm working degree by degree. Remember, in my story, I said that these numbers Vi for the type 2 quivers were all proportional to Dynkin labels with one. So there was one integer which could be arbitrary in this problem. And so if we fix n, then here we deal with degree n quasi-maps. And here we deal with the holomorphic G bundles on P1 cross E with fixed second chain class, which is n. Okay. Now, so I probably have 2 minutes. Okay. So now let me go to the conclusions. So far, I described the asymptotics of this partition function when both epsilons go to 0. This asymptotics is it's sort of a generalization of the problem in asymptotic representation theory of symmetric group, which Vershik and Kerov worked on, and Logan and Shep found a limit shape for the. So the simplest case of which would correspond to the quiver of A1 type with the trivial space W. This is the Vershik-Kerov limit shape problem. But now we had actually, the suspicion is that this full partition function, not only its asymptotics, has a nice geometry. And indeed, it turns out that if epsilon 1 is finite and only epsilon 2 is sent to 0, then this story, which I just described with the characters of ordinary Lie groups or Kac-Moody groups being equal to polynomials, is deformed in an interesting way to the story of, so this element G of x, which was an element of the Lie group or Kac-Moody group, becomes an element of a Yangian built on the same root system, or quantum affine algebra in a 5-dimensional case. And so this equation becomes a difference equation for the functions y, not an algebraic equation anymore. And in the case of A-type quivers, So the difference equation can be Fourier transformed. It will produce for you the opers, GLN opers on P1 with punctures or elliptic curve with punctures. With the regular singularities of prescribed type, yeah. But you call them opers because you view them as GLN flat connections. And it's the monodromy data of these opers which encodes the asymptotics of this function z in this case. Now, in this case, you can actually go to the full partition function, and then it turns out that these opers are, in turn, the limits of the equations obeyed by conformal blocks of Liouville theory or Toda theory on these Riemann surfaces, the genus 0, genus 1. And so in this case, it has been shown, actually, that for the A-type quivers, these both affine and finite, this partition function z is equal, exactly equal to the conformal block of the of these theories, Liouville or AN minus 1 Toda. Now, if we are dealing with the, and so this fact has a following geometric counterpart, namely this modular space of bundles on a surface P1 cross elliptic curve. If this, for the group G, which is of the A type, is isomorphic, is symplectomorphic actually, to the modular space of, to the Hitchin modular space for the GLN Higgs pairs living on a dual elliptic curve with punctures. And the number of punctures depends on the rank of this group. So, and so the opers actually live in as a Lagrangian subvariety in this Hitchin modular space. So this fact that for the A-type quivers, you can actually collapse this 4 real dimensional geometry down to a 2-dimensional one explains, or it's related to the fact that this full partition function can be described in terms of a 2-dimensional conformal field theory. However, for the D or E-type quivers, there is no such transform. There is no such Fourier relation which would replace bundles on the surface by something like a Higgs pair or something which would live on a lower dimensional curve. And so in this case, it is expected that these partition functions will be described by, in terms of representation theory, of something higher dimensional, like a double loop algebra or something like that. Thank you.
These questions, I ask why.
Because this is a two-dimensional surface.
Well, I have the line of EPS mentioning an actual wall crossing. Is there some story?
Yes. Well, that story starts when, so in studying this Z partition function, I did arrive at some holomorphic symplectic manifold. But actually, in truth, and you can actually see from already here, this holomorphic symplectic manifold actually has a hyperkähler structure. It's a hyperkähler manifold, which you can describe as the modular space of G. So this is compact instantons on R2 cross T2. And then you can try to describe all complex structures on this hyperkähler manifold. And in particular, you can try to coordinatize it. And the fact that in the A-type case, we have So this modular space is isomorphic to the modular space of local systems on elliptic curve with punctures, which has several systems of interesting Darboux coordinates, in particular for Goncharov coordinates, whose construction is related to the wall crossing phenomena. Suggests that there should be similar, or I don't know, there should be some set of special Darboux coordinates described directly in the four-dimensional terms. And so there you would expect to see this wall crossing structure.
So suppose we take fever just one point.
Yes.
Then we are dealing with this instant-on moduli space.
Yes.
And you have a generating function for the push forward of the tautological bundle
Yes.
on surface.
Well, it's also addressed with so even for A1 quiver, you still have a space W, which is do you have W or you don't want to have W in your question?
The generating function.
Yes, it depends on W.
Right. So for one point, so does it give a nice expression for the generating function? Can you calculate the?
Well, in general, these are truly non-trivial functions, so you cannot write them in a closed form, except that when except when the dimension of the space V is 1. So if actually it's also a nice relation to yesterday's section. So if gamma is of A1 type, so just one vertex, and V is one-dimensional, and let's say W, so W in this case can be up to at most 2. So you have two parameters in the problem. So you have a matrix with two eigenvalues, M1 and M2. And then the partition function actually can be calculated explicitly. It's not too, I may be making a mistake, but I think it's something like that. And also, it's essentially, well, it depends on, sorry, Q is, we have one Q parameter in this case, and there is A squared over epsilon 1, epsilon 2. So A, it's this matrix. If A has a trace, you can shift it at the expense of shifting M, so it's interesting. But what's interesting is that in this case, you can also come, this function y, which I talked about, is interesting. And so y solves the equation in case when epsilon 1 equals epsilon, epsilon 2 is equal to 0. It solves the following equation. And it might look like a complicated equation, but in fact, its solution is a ratio of hypergeometric functions f to 1 with some shifts of the indices. So the hypergeometric function makes an appearance here.
So you just erased it. Yes. So you have these bundles on P1 cross P
Yes.
trivialized somewhere.
Yes.
Can you somehow draw what happens when you collapse this somewhere to a point?
Well, this somewhere is elliptic curve. So how can you collapse it?
You can collapse any subset of any power.
Maybe we should discuss it separately. What you can do, you can degenerate elliptic curve. And so you make it a sphere with 2 points glued together. Then you get to to the type 1 story, which I didn't describe in detail.
Okay, so thank you very much for a wonderful talk. 50 from 10, 55.